Hi there, Advanced Hire. This is my effort at going through the PowerPoint with you. I said I would give it a shot to try and simulate what it would be like in class and listen to me trying to explain some of the slides for you. Some of you have already went ahead and done the tutorial, which is good. I would ask you to listen to this again just to kind of get any more explanations you need for the slides. So over the next week or two, I want you to look at quantum theory. And there's a tutorial on that, only one tutorial, not two tutorials this time. I'll be giving you an assessment on this on Thursday, just a kind of check test, and next week I will give you a kind of past paper assessment on it as well, just so we make sure we're up to speed with what quantum theory is. As always, please get me any questions on the Teams, or email me anything you've got for me. Mrs McLaughlin will also be able to support. Some of you should know Miss McLaughlin from last year. She's taught Advanced High before, so she might pop on the team to answer any questions that you've got. I'm also free to do a video, a team video or something if you want. If you're needing any particular questions answered, I'm happy to do that on Teams as well. Just let me know if you want me to do that. Okay, so we're going to start talking about quantum theory. I'm just going to talk through the slides and you can get back to me if there's any issues that we've got. I've tried to include the page numbers on it, and I'll add the page numbers to the assignment as well to let you read through it, and I would encourage you to do that. So, quantum theory refers to long-standing explanations of the world around us. These theories, for example, Newton's laws, can be used, classical theory refers to long-standing explanations of the world around us. So classical theory such as Newton's laws explains what we can see, what we can hear, generally what is a kind of human-sized things, the world around us, basically what we can see. As we get to things really big, it starts to become the size of planets or the universe, the galaxy. These classical laws don't really work anymore. And you've seen that a little bit when we did the astrophysics unit. And how the universe stays together. It's not really classical physics. As we go to the other end of the spectrum, things that are really, really small, we end up dealing with quantum theory. Now, quantum doesn't mean small, but you may be familiar with quantum realm. They used that in the Marvel movies. Ant-Man and the Wasp, they talk about the quantum realm. The quantum realm just means, it does refer to things that are very, very small, but quantum doesn't mean small. So what it means, so when we're talking about electrons or particles inside the atom, or how the atom interacts, or kind of very, very small things, we tend to talk about quantum. Now, quantum means a packet, or a quantum of information, or a quanta, or to quantize means a small packet of something. So quantum theory refers to a group of explanations that can explain observations that classical theory cannot. What links quantum theories is that they all involve the use of packets of small constant numbers, such as Planck's constant, mass of an electron, charge of an electron. All these things are quanta, or amounts of information, little packets. So although quantum does refer to things that are very small, quantum itself refers to a packet, such as Planck's constant. We're going to use Planck's constant quite a lot. Now, you need to be familiar with the theories that require quantum explanations, and there are 4 standard ones that you could be asked for in an assessment. There is blackbody radiation curves, the Bohr model of the atom, de Broglie wavelengths, and the photoelectric effect, which is part of wave-particle duality. Now, I'm going to go on and explain all 4 of these and the wave-particle duality, and it's quite a lot of theory. There is some formulas involved which you'll find in the tutorial. That's why there's only one tutorial, but most of it is theory. You could be asked a long answer question on this, and I will find some long answer questions in past paper questions for you to answer, probably either this week or next week. So let's just move on, and I'll talk about each of the standard observations, and if you could maybe take notes on this, or do whatever you do in class to try and learn it as best you can. There are lots of extra videos I've added onto this. It's a very complicated part of physics. I would encourage you to do that and read the textbook pages to try and get yourself up to speed with this. So the first one is called blackbody radiation curves. You find this on page 58 of your textbook. And this refers to I'm just going to get a pointer ready, here we go. This refers to the radiation curve that you would see with black body radiation. So black body radiation is a name given to radiation that's emitted by hot objects. It's called black body because an ideal radiator of heat that only releases heat doesn't release any light, so it's known as a black body. So classical physics governing black bodies basically says the shorter the wavelength, the greater the frequency, the more intense the radiation would be. And this is what the Rayleigh-Jeans explanation, Rayleigh-Jeans law states. So what it says is as you get lower down the wavelengths, the energy or the intensity or the radiation you get should increase. However, it doesn't. And this is a failure of classical physics, it's known as. And what actually happens is as you get further down the wavelengths, the energy peaks round about here and then drops off back down. You'll be familiar with this curve from higher. You did this at higher, and it's about the peak wavelength, the amount of energy produced by stars, all that kind of stuff as well. So this failure of classical physics to explain the evidence is referred to as the ultraviolet catastrophe. So what it means is that this is the law that's supposed to stand. It doesn't stand. This is what you do actually get, and because as the wavelength gets towards the ultraviolet end of the spectrum, it doesn't reach infinity, then that's known as the ultraviolet catastrophe, because the irradiance does not go to infinity as the wavelength approaches the ultraviolet range. So classical physics can't explain it, and we have to use quantum theory to explain it. Now, the quantum part comes in because of the E equals hf. Okay, so Planck's constant is used to quantize the black body radiation using E equals hf. At large values of frequency, small wavelength, the energy is too big to be possible. It's too big. So E equals hf says that as you lower the wavelength down to this end here, the energy becomes so big that it's not going to be possible, because this goes to infinity. It goes to an almost infinite energy, which we can't have, and so therefore it's been quantized. We quantize this explanation. It's a quantum theory, and we use E equals hf to explain that. The next one is the Bohr model of the atom. Now, I'll take the video out of the way so you can see the theory here. Classical physics suggests that an orbiting electron experiences a centripetal force and an acceleration towards the nucleus. Classical physics also predicts that an accelerating electron will irradiate energy and therefore spiral inwards as the energy decreases. Okay, so what it's saying is that as electrons orbit, like all orbiting bodies, such as a moon, not necessarily a moon, a satellite orbiting a planet, what happens is it loses that momentum, it loses that energy, and would eventually spiral down towards the centre. So if you leave a satellite orbiting around about a planet, eventually it will orbit and fall back down to Earth, and we need to boost it up every so often to do that because of friction, because of the friction of the atmosphere. Electrons don't do that. So they don't spin in as their energy decreases, and they don't fall down. So Bohr came up with, it was actually Rutherford and Bohr, came up with this model which describes the electrons orbiting only in certain allowed orbits with certain amounts of energy. So they are being quantized. The energy of each orbit is a quantized value because it's h over 2 pi. Electrons can jump from one allowed orbit to another. The electron must gain energy when it jumps to an orbit, an outer orbit. An electron is given off when it jumps, and an energy is given off when it jumps from an outer to an inner orbit. Now, angular momentum, MVR, which you know of, we can then replace that with nh over 2 pi because that is how we quantize the angular momentum, and that's a formula we use for the Bohr model of the atom. So the next one is the de Broglie wavelengths. You find this on page 62 of your textbook. Now, the de Broglie wavelength is a step up from the explanation we use for the Bohr model of the atom. And you may have heard me talking about the fact that electrons have a wavelength. Now, we're going to go on and talk about how electrons behave like particles and wavelengths. But when we talk about the particles themselves as they orbit around the atom, you maybe learned about energy shells or energy levels, but what's really happening is the electron stores its energy in its wavelength and its frequency that it has as it vibrates around about the centre of the nucleus. Now this is what the electron orbits look like. If it's got 1 value of wavelength, then it orbits like that. 2 would be like that. 3, you start to see there is a wavelength appearing here. 4 wavelengths, 5 wavelengths. The more energy it has, the more it vibrates. So Louis it's spelled de Broglie, but it's actually pronounced de Broglie, proposed that since particles behave like waves, then all particles must have a wavelength. This wavelength, known as the de Broglie wavelength, is extremely small. Within the Bohr model of the atom, allowed electron orbits must have an exact number of de Broglie wavelengths fitting into the circumference. The higher the electron orbit, the shorter the wavelength, the larger the frequency, and the greater the energy, because E equals hf. So de Broglie proposed that wavelength applies to particles and waves. So this is part of this, how waves and particles are very similar. We're going to talk about that in the wave-particle duality part. But you can work out the photon energy because E equals hf, but F is also c over lambda. So Einstein's energy mass relationship equals mc squared. You combine all these together and you end up with a formula for the momentum of an electron, which is h over lambda. And this is the de Broglie wavelength of the electron, and it's been quantized, a quantum formula, because you've got that packet of Planck's constant once again. So this takes us on to the last part, which is wave-particle duality, which encompasses the photoelectric effect. We have so wave-particle duality, which is on page 62 of your textbook, discusses how particles and waves can behave in very similar ways. Now this is not to say that every wave is a particle, every particle is a wave. It's just that they can behave in similar ways. Some particles can. So EM waves and radiation, including light, can produce interference, reflect, refract and diffract. That's your definition of a wave. Waves do not have mass and cannot be accelerated. Waves can transfer energy based on their amplitude. That's all of the kind of standard definition we have for what a wave is. However, particles, including electrons, have mass and can be accelerated. They cannot cause interference, reflect, refract or diffract, or so we're told. This is the basic definition of what a particle is. This is the definition of what a wave is. Now, these are the classical definitions. However, they can't explain everything. They can't explain some of the behaviours that we find, and we use quantum theories to explain this. Most of them have packets of energy inside them, packets of little pieces of information, hence they're called quantum, to explain observations where waves can behave like particles and particles can behave like waves. And those situations where waves and particles behave similar to one another are known as wave-particle duality. Now, these observations involve EM radiation, usually light, and electrons. So we're talking about photons and electrons. Refer to EM radiation and electrons exhibiting wave-particle duality. So electrons and EM radiation exhibit wave-particle duality. So there are 3 pieces of evidence for wave-particle duality: electron diffraction, the photoelectric effect, and Compton scattering. Now, the photoelectric effect tends to be the one that we use to explain quantum theory as well. So we'll just go through the 3 of those and explain what they are. So the first one is electron diffraction. Basically, when you pass an electron through a thin graphite screen, thin carbon disc, which is this part here, you get this pattern produced. Okay, now what we're observing in the pattern is we're seeing diffraction occurring. If you pass a very fine stream of electrons through a thin piece of graphite, the electrons diffract and cause an interference pattern. So these green circles here refer to the interference pattern caused by the electrons diffracting through the disk. Just like you would get a photon diffracting through thin slits and causing an interference pattern here as well. So this is an interference pattern caused here. An interference pattern is a test for a wave. So therefore, an electron is a wave. So wave-particle duality. Electron diffraction is evidence of wave-particle duality. Photoelectric effect, which we did at higher, it's summarised again on page 59 of your textbook. So we talk about the light if you remember from higher, the photoelectric effect is when a photon strikes a piece of metal and causes an electron to be emitted. Photoelectric effect or photoelectric emission, photons calling an electron to be emitted. So light falling on a metal plate can cause electrons to be emitted from the metal plate. This is known as a photoelectric effect. This process is called photoemission, and electrons emitted are known as photoelectrons. So classical physics can't explain this. It can't explain why the intensity of the visible light cannot. So basically classical physics says that the more intense we make the photon, so if we make this photon high energy, the higher the energy we produce, this photon, the more electrons will get off. But what we found out, and what I showed you would have seen in class and higher, was that ultraviolet radiation can, but normal visible light cannot. So if you have a high intensity visible light, according to classical physics, it should emit an electron because it's got enough energy to do that. But it doesn't. Ultraviolet light, which has the correct frequency, allows the electron to come off. So there's that threshold frequency. Remember the work function, threshold frequency from higher, is required before photoelectric emission can take place. So read through the rest here. Classical wave theory predicts that a bright source of light has a large amplitude and a large associated energy, therefore should have enough energy to cause photoemission. Classical wave theory also predicts that weak ultraviolet light will cause photoemission, but there should be a delay as the energy builds up. There's no delay, and visible light doesn't cause it. So the classical physics can't explain photoelectric emission. However, Einstein then used Planck's quantum theory for blackbody radiation and took it further to explain photoemission. All EDM radiation is made up of discrete quanta of energy. The minimum energy required for photoemission is called the work function, and the associated frequency the threshold frequency. So we bring in these packets of energy, Planck's constant, and we prove that there is a minimum energy required. There's a small packet of energy required in order to make this happen. Okay, read it up, page 59, and watch some of the videos. You'll see a bit more explanation in this. But you just need to understand that photoelectric effect is evidence of wave-particle duality and evidence of quantum theory. Right, the next one is known as Compton scattering. Now I'll just take away the video again. Experiments carried out by an Arthur Compton provide further evidence of the particle nature of light and wave-particle duality. It was observed that when a photon collides with an electron, the electron and photon are scattered in different directions. So, photon comes in and strikes an electron. Now, the photon is then goes down this way, and the electron then goes this way. So, this is much like if you think about, say, a snooker ball getting struck by a cue, or a snooker ball struck by another ball. They can deflect one another and they can go in different directions. So the scattered photon has a frequency less than the original, proving that its energy has been absorbed by the collision. Now, energy being transferred during collisions only happens when materials have got mass. So if a photon doesn't have mass, then how does it lose some of its energy in a collision? The reason is because it behaves like a particle as well as a wave. So this E equals hf, and this fact that this is a larger wavelength, a lower energy, proves that it behaves like a particle because it has lost some of its energy. The collision also confirms to the conservation of linear momentum as it would do for particles. So linear momentum saying, well, the amount of energy before the collision, the amount of energy afterwards, the amount of momentum before and afterwards, all to do with linear momentum. Again, proving that waves and particles have wave-particle duality, electrons and photons. Okay, so that finishes off the part on quantum theory and the wave-particle duality. And the last thing we're going to look at this week is something known as the uncertainty principle. Now, those that watch Breaking Bad will be familiar with Heisenberg. And Heisenberg is responsible for this uncertainty principle. He's the person in charge of it and who came up with it. So let me quickly run through this for you. It's actually not as hard to understand as you might think, and let's just quickly talk through it. So the existence of the de Broglie wavelength results in quantum particles never being in a fixed position. So what we're saying is electrons always are vibrating. They're always oscillating back and forward, back and forward. So they're never in a fixed position. So if we want to know exactly where a particle is, we don't. We don't know exactly where it is at a particular moment. We can estimate where it is, but we never know exactly where it is. So since position is uncertain, then so is velocity and so is momentum. So if the position of the electron is never certain because it's oscillating back and forward, then its velocity can never be certain and its momentum can never be certain. The Heisenberg principle states that it is impossible to predict accurately both the position and the momentum of a quantum particle at the same time. This can be explained using single slit diffraction, where delta, this is delta, refers to the uncertainty of the quantity. So here we have two different examples. We have diffraction, we're going to explain it. So we have diffraction with a large slit and diffraction with a small slit. So if we use a wide slit diffraction, there's a high degree of uncertainty in the position of the quantum particle across the slit. We do not know where the quantum particle is at any one time. It could be anywhere in this slit as it bounces back and as it bounces through. However, we do have a high degree of certainty in the direction, because we know it goes in and leaves that way. So if it comes in here, we know for certain it's going to keep going straight, because there's a wide slit and there's nothing to diffract it around. So the position is uncertain, but the direction, the velocity and momentum are actually quite high. So its position is uncertain, but its momentum and velocity are quite certain. So its uncertainty in its position and velocity is low, its uncertainty in its position is quite high. If we use a narrow slit analogy, we've got a narrow slit here, we have more certainty over its position because we know it's got to be in a smaller area, so its uncertainty is therefore smaller, but its momentum and position, its velocity is now less accurate because we don't know when it leaves where it's going to be, because the direction of the leaving the slit has changed due to diffraction. Exact velocity has become less accurate, therefore the uncertainty here in the momentum and velocity is greater, however position is smaller. So that's the Heisenberg principle for you, and there's some questions in that I think in your tutorial as well. So the last thing that we have this week is looking at quantum mechanics. We've talked about quantum theory, so we'll link it all together with something known as quantum mechanics, which is another quite an interesting term that we've dealt with and you might get heard of. So we have done the uncertainty principle, the Heisenberg principle, and quantum mechanics is the study of quantum particles such as electrons and photons, and it deals with probabilities and uncertainties. Probabilities of position, probabilities of momentum, velocity. So momentum is really velocity. It's the same kind of thing, mass times velocity after all. So the product of the uncertainty in a quantum particle's position and momentum must always be greater or equal to the stated value of h over 4 pi. So the multiplication of the position and the uncertainty in the position and the uncertainty in momentum must be greater than or equal to h over 4 pi. Hence, here's your quantized part. Here's the fact it's h over 4 pi. It must be a multiple of that amount of energy. So the energy of the particle and the uncertainty in the time taken is another part. So this is the part which you've been explaining in terms of Heisenberg. This is the next part, which is a kind of extension of that, is the uncertainty in the energy and time. So this is uncertainty in the position and momentum. Here's your uncertainty and energy and time. One must be high, so really this one as well, one must be high, one must be low. This one must be high, one must be low. Uncertainty and energy of the event and the uncertainty in the time taken. So we've described this one. I don't need to go through the description of this one, we can use the formula. This one here, so given the uncertainty in one of the two quantities, the least uncertainty in the other can be calculated. So we simply take whatever one we're trying to calculate and we put the other one underneath the formula, so that there. So the uncertainty in the position, delta x, is equal to h over 4 pi delta p, where you have the uncertainty in the momentum. You can use this formula to answer quantum mechanics questions in the tutorial. And the last thing is on quantum tunneling. Now this is really quite complicated as well. Now, those of you that are familiar with again, the Ant-Man movie or the Ant-Man and the Wasp movie, the sequel to it, there was a thing about the quantum realm, and the baddie in the movie was able to pass through walls. So if you remember, those that have seen the movie, the Ant-Man and the Wasp, the baddie is kind of in flux and is oscillating back and forward, and you don't get a clear image of them, and they're in flux, so their position is actually uncertain at all times. It's all to do with Heisenberg principle. So what we're saying is that because the probability of their position is so high, then if you place a particle with a high probability of position near a barrier, now we're not really talking always about physical barriers such as walls, but we could be, but it could be on either side of the barrier. So if the probability, so let's say this is an electron, an electron is oscillating back and forward here, then, and we put it next to a barrier, not necessarily a physical barrier, but as we know, electrons can pass through physical barriers if they're thin enough, or maybe there's evidence of more than that, but for now, it could be a thin barrier. The probability is that the electron could be on the other side of the barrier. The electron could pass through the wall, if you like. So high probability that's in the middle, but it's also low probability that's on the outside as well. So the probability nature of quantum particle position allows for quantum particles to cross energy boundaries without seemingly having enough energy to do so. The position of a particle is a probability around a certain point, therefore it is probable, no matter how small, that if a particle is next to a thin enough barrier, then the particle may already be across the barrier. Get your head around that one. This is referred to as quantum tunneling, where potential energy wells from barriers form barriers which would not normally allow particles to escape. Borrowing energy for a short period of time allows particles to escape from potential well. That's the complicated part. There is a lecture video on this to help you out. Where the energy is borrowed from is not clear. It could be the barrier itself, the surroundings, the vacuum, or the universe. The borrowing of energy from a vacuum also allows for particles to appear in space for short times where there classically are none, called virtual particles. Now this kind of bottom section here is all quite kind of theory based. I think the main thing is that you know the probability that it could be on either side of the barrier. High probability that it's not, but there's a low probability that it is. I will add these two web links to the assignment, and I'll also add this video to the assignment. Good luck with your task for this week, and as I said, I'll be adding on additional assessment questions for this week, and we'll see you again next week.